prove, we said yesterday, this is super cool proof, different kind of proof, so I want to show it to you. We said yesterday that we knew a couple limits, right? There's some special limits, some trig limits that we can use to eliminate the indeterminacy of trig limits. What's one of them? The limit of what? Over what?
Sine theta over theta equals theta.
Okay, that's theta approach to 0 equals 1. Okay. And then another one we get from that. Remember what it is?
We need the 1 minus cosine theta over theta is theta 0, 0.
Okay. So let's take the top one, because if we know the top one, we can easily prove the bottom one. Okay, here's how we're going to do this. We're going to do a geometric proof. Kind of a sort of a geometric proof, yeah. Let's call this angle theta. We're going to draw 3 areas, compare the areas. Okay, let's compare the areas. We'll kind of try to color code these two, how about? So one of the areas is going to be this little triangle right here. This is a unit circle. Okay, so I want to come up with the area of that triangle in terms of theta. Help me out. Okay, so this equals 1. Good. And what's equal to the area of a triangle is what? 1/2 base times height. Okay, good. So we would need to know somehow here. We need to know some stuff, right? Base of the height. Okay, suggestions.
You know the base is less than 1 because it's a circle.
Mm-hmm.
It's on 1, so it's...
Mm-hmm. Good. Okay. What else can we do with that?
The sine theta equals 1 over x, I guess, and what variable we put for the sides, 8, I guess.
Okay, so say it again.
Sine theta equals, like, isn't it 1 over a or a?
So by SOHCAHTOA,
Yeah.
right, by SOHCAHTOA, we know sine is the ratio of what two things?
Yeah, yeah.
Opposite over hypotenuse? Okay. So then we know that the sine of theta equals, let's just temporarily call that h for height. How about it? Okay. Equals h over 1. So what's h equal to?
Sine theta.
Sine theta, right? So if I take this blue triangle, and let's just, to be convenient here, let's just move it down here for a second. So my blue triangle then, if that's theta, that's 1. That's sine theta, right? Everybody agree? Okay. And what's going to be the bottom then? Call that width, for width, I guess, right? What's the trig function that relates those two? Cosine? Equals adjacent over hypotenuse equals width over 1. So that's really just equal to cosine theta, isn't it? Everybody agree? Okay.
Special kind of triangle.
What is sine?
It's tangent theta, right? Okay. Okay, so what are we going to do then with with this, what are we gonna do with this?
We're giving the unlimited.
So I mean tangent data is literally tangent data, not triangle.
Oh. You're the wrong triangle. No wonder. Yeah, what we did is still good though. I just gotta go back and redraw this triangle, so. Yeah, it's a good triangle. No wonder. It's a good triangle. No wonder that would be wrong. Okay, so here's the triangle we want. We want this triangle. It's all the way to there, and then up to there. Okay, agreed? So it's an isosceles triangle, isn't it? Let me tweak it down here too, so it's gonna look like. Okay, you'll see why we're doing this in a second. This will be better. So kind of like, I didn't draw that very well. But now this triangle is a little easier to deal with. What's gonna be the length of the base? 1, right? Great. Okay, so the length of the base is 1. Now what about the height? Here's my height. Okay, what about the height? To find the height, let's consider for a second, let's consider the triangle we looked at before. Let's just look at this little right triangle instead. Okay, so maybe we'll shade that light. Okay, if we look at that little right triangle, this is a great little trick in that. They're different triangles. The light blue and the dark blue triangles are different, but they share the same height, right? So if I can find the height of the easier light blue triangle, I'm also finding the height of the slightly more complicated dark blue triangle. Agreed?
It's still fine.
It's sine theta though, isn't it? Right? Because wouldn't you agree that the light blue triangle has a hypotenuse of length 1, and so the height must just be sine theta, as we previously discussed? Everybody agree? Okay. So then, if that distance right there is sine theta, and the base has a length of 1, what's the area of the blue triangle?
It's half sine.
It's, yeah, 1/2 times the base, which is 1, times the height, which is sine theta. So sine theta over 2, 1/2 sine theta or sine theta over 2. Everybody agree? So let's call that a sub 1, how about? That'll be blue. A sub 1 equals sine theta over 2. Okay. We're going to look at another shape now. The next shape we're going to look at is going to be this sector. So it's going to be this piece of pizza that describes an angle theta. Okay. What do you suppose the area of the sector is going to be?
Wait, so is the pizza the whole?
The whole orange piece, yeah. So slightly bigger area than the blue triangle. Everybody agree? Because we're filling in this little bit of extra area there. It's really just the blue triangle plus that little bit of extra area. Okay? I want you're not going to remember this formula probably from last year. We do have a formula for the area of a sector, but you should be able to just come up with it.
That's the arc one, isn't
It is.
it?
Well, okay, it's not arc length, it's actually area of the sector. So would you remember what it is?
Theta equals S over R.
Theta equals S. Okay, good. That's one way to do it. So we could say, good. Theta equals S over R. Okay. So then what's the arc length in this case? If I solve for S.
S equals 1.
Well,
R times theta.
R times theta, but what's R?
1.
1. So in this case, S equals theta. Okay, we agree? But that's not what we're looking for yet. We're looking for the sector area. You may not remember the formula for sector area. I'd probably, if I hadn't thought about it in a while, I probably wouldn't either. But I could always figure it out on my own. There's a way we could do this. We should be able to set up a proportion here.
Oh, so, just, like, well, so we just do the proportion of the sine theta of the side, no?
Forget about the blue triangle for a second. Just think about the orange sector, the orange piece of pizza. That should be a predictable fraction of the area of the whole pizza. And the area of the whole pizza we should be able to calculate, right? We know it, everyone knows that formula. That's just the area of a circle, right? Everybody agree? Okay, so what fraction is the orange area of the area of the whole pizza? I'll remind you, that angle is theta.
That's like a fraction, is it?
No, that's important though. It's gonna depend on theta, obviously, right?
Is it theta 2?
Oh, no, you're onto something. What are you gonna say?
I was looking at the area first.
Don't look
Oh,
at me.
that would make sense, so, when, but, no.
You're not gonna be able to give me a specific. When I say predictable, we don't know how big theta is, right? Theta could be pi fourths, theta could be 11/16 pi, it could be anything, right? It's just theta. But in terms of theta, you should be able to define the fraction of the total area of that pizza that's represented by the orange sector.
The base of the proportion would be sine theta over something equals theta over something, right?
Say it again?
Sine theta over something equals theta over something.
You don't need to sign in there at all. There's no signs. Just forget about the blue triangle completely. I could have just started with this, with a sector. The orange sector is gonna be what fraction of the area of the.
radians.
Yeah,
Yeah.
okay. How many radians would describe the complete circle all the way around? 2 pi, right? Everybody agree? So then what fraction of, now I don't want the answer, I just want the ratio here. What fraction of the total area of the pizza is represented by the sector? What out of 2 pi? Theta, right? Everybody agree? Doesn't that make sense? Okay. If we were to expand this, if somebody was really a pig here and their piece of pizza or their slice represented the whole pizza, well then that would just be 2 pi r, right? Would be the area. I mean, no, it's not. Sorry, no, it's not. What would it be? What's the area of a circle? What is it?
2 pi r.
It'd be pi r squared, right? It's the area of a circle, right? Okay, but we don't eat the whole thing. We just eat some fraction of that. But what fraction of that are we eating? Well, we're eating
So it's theta
theta
over 2
out
r
of
squared.
2 pi radians of that pizza,
So
right?
theta over 2r squared.
Okay, so then what we're gonna get is the fraction, once again, the fractional area of the sector is just theta out of 2 pi, right? Everybody get that? So A sub S for sector, how about? Equals theta over 2 pi, and that represents fraction of whole, right? Everybody with me? Times the area of the whole. Should do it, shouldn't it? The fraction of the whole times the area of the whole should give me the area of the sector. And you already told me that the area of the whole is just pi r squared, but what's r?
Radius
1, right? So this is just equal to theta over 2 pi times pi, right? We agree? Which works out to be what?
Theta over 2.
Theta over 2. Okay. So theta over 2 is the area of the sector. Agreed? Okay. Let's look at one more triangle here. Let's look at, make this one green. Let's look at the big triangle.
Wait a second. Wait, so back to the first thing that I said that was wrong.
Mhm.
Arguably, is it right?
Which
Because I originally said sine theta over something equals theta, and the area is sine theta over 2. And if you plug 2 in, or is that just coincidence?
Coincidence.
Coincidence, okay,
Mhm.
yep.
Yep.
Sweet.
Okay, so now if we look at this green right triangle, let's find that area. What do we know about the green right triangle? How about if we just redraw it up here? What do we know about that one? We know one side, don't we? What's that?
The base.
Base is 1. Okay, so if we just knew the height, we could find the area, correct? Everybody agree? Okay, how are we gonna do that?
No, the angle is theta, so would be
Yeah, in your theta, right? So do we know
so we
Do we know a trig function? We know this side, we're seeking that side, right? Do we know a SOHCAHTOA trig function that relates those two sides in a right triangle? Tangent, right? What's the definition of tangent?
sine over the
Okay, but in terms of SOHCAHTOA stuff, in terms of the sides of a right triangle.
Opposite
Uh,
Opposite.
Opposite over adjacent, right? So that's gonna be the ratio of opposite, which we'll just call y, how about, for the height? Does that sound good? So if we call that y, it's y over 1. So what is y equal to? Tangent theta, right? Okay, so when we draw that, when we go up and draw this triangle then, in terms of theta, that's tangent theta, right? Okay, so what's the area then of the green triangle? Okay, yeah, 1/2 the base times height, so tangent theta over 2, 1/2 tangent theta, same thing as tangent theta over 2. Okay, now let's call this one, I'm gonna change my naming structure a little bit. I'm gonna call this A sub little t for the area of the small triangle, right? We got the area of the sector, and now we've got the area of, I'll call it capital T, the area of the big triangle. Okay? Would everybody agree that regardless of what theta is, it's independent of theta, no matter what I pick for theta, there's gonna be a discrete recognizable hierarchy of areas, order to the areas. What's always gonna be the smallest of the three, blue, orange, or green? Blue. What's always the middle one? Orange. What's always the big one? Green, right? Everybody agree? So then we should be able to set up an inequality here, right? We should be able to say that, let's go, I'm gonna do it backwards for a second. Let's go, yeah, this will work better. So A sub capital T is always gonna be greater than A sub S. Oops. And that's always gonna be greater than A sub little t, correct? Okay. What's the one case, would it always be greater than? Could be equal to though, couldn't it? What would be the case if we look back at our picture where maybe they could be equal?
It's 360, or 2
Or
Theta equals 2 pi.
what if we limit theta to be, let's just say between 0 and pi half?
If it was pi.
If I shrink theta down to 0, then they'd all converge on 0, wouldn't they? Right, everybody agree? So I should probably go back up here then and do that. Agree? So let's plug in those expressions. So we ended up with, this was tangent theta over 2. Right? Everybody agree? Okay. This was theta over 2, and this one was sine theta over 2. Agree? Okay. So we're going to do something here. Tangent is the same as sine theta over cosine theta, right? So I'm going to rewrite this. Okay. That's always the case. Anything we could do here to maybe simplify this compound inequality? What can I do? Multiply everything by 2. If I multiply all expressions by 2, I preserve the order though, right? Everybody agree? Okay, so we could, that's convenient, we could do that. Okay. Now I'm going to do something a little weird. Let's go ahead and let's divide each one of those by sine theta. Okay, if we limit sine theta, that might seem a little strange, but if we limit sine theta to be, let's just say arbitrarily to make things a little easier, let's limit sine theta to be between 0 and pi halves. Okay, agreed? If I limit sine theta to be between 0 and pi halves, sine theta is always, or theta to be between 0 and pi halves, sine theta is always positive, isn't it? Agreed? So if I divide each of these quantities by sine theta, or multiplying by 1 over sine theta, same thing, I should also preserve the order, because I'm multiplying by the same positive number. Agreed? Are you with me? Okay, I can do that. So if I do that, if I divide each one by sine theta, what does this guy become? Well, okay, if I'm multiplying by 1 over sine theta, maybe I'll do that. Let's go ahead and write that out. What happens? Sine thetas cancel, right? And I get 1 over cosine theta. Now what's going to happen here? I multiplied by 1 over, whoops, sine theta. So that one's just going to become theta over sine theta, right? And this one is going to become 1, isn't it? Right? Okay. What would happen if I were to take the reciprocal of each of those expressions? Well, what would have to be true then? What's that going to do? If I know that each of these expressions has to be greater than or equal to 1, right? So if a fraction has a value greater than 1, and I take its reciprocal, what happens? Becomes what? Like say 5/4. It becomes smaller than 1, agreed? What's going to happen to the order of these things then? If this fraction is always going to be either the biggest or they're equal, right? But this is, if we look at the areas, as long as we don't choose 0, this is the biggest fraction, isn't it? This is the second biggest, and this one is 1. If I invert them, the biggest fraction becomes the smallest fraction, right? The middle fraction stays the middle fraction, and the biggest and the smallest fraction is going to become the biggest. Make sense? Okay, so here's the step we're going to do then. We're going to flip all these around, and we get cosine theta over 1, sine theta over theta, and 1. And I got to change each of those signs then, right? You with me? Okay, good. So that's an expression that's a compound inequality that's always true on our interval from, let's say, 0 to pi halves, right? Okay, let's go ahead and do something though. Let's take the limit of this as theta approaches 0. Okay, what's going to happen if I do that? If I take the limit of each of these expressions as theta approaches 0, then I should get, all I'm doing is I'm just shrinking theta down towards 0. It's still positive though, right? So we'd end up with the limit of cosine theta as theta approaches 0 is still going to be our left boundary. The limit sine theta over theta is pinched in the middle, and the limit of 1 is going to be our right boundary. Well, let's evaluate those limits. What's the limit of cosine theta as theta approaches 0? 1. Oops. What's the limit of 1 as theta approaches anything? 1. Okay, so you tell me then. What's the limit of sine theta over theta as theta approaches 0? Has to be 1, doesn't it? If that has to be greater than or equal to 1 and less than or equal to 1, it's 1, right? And what's our reasoning for that? It's something called the sandwich theorem or the pinch theorem. We call it either one, which just looks like this. But this will make sense. If I've got on some interval, the big one was the back here. So we had the blue was the big in this case, green was the small, orange was the middle. Okay. So if we have some big function, some smaller function, some even smaller function, such that the limit of the big function and the limit of the small function both approach the same value at x equals c, then doesn't the orange limit have to get pinched to that value also? Right? I'm not going to write out all the words, you can look in your book, but here's what the words would say. If on some interval surrounding c, we'll call this one, how about f of x, whoops, g of x, and h of x. If on some interval surrounding c, f of x is greater than or equal to h of x, or h of x is greater than or equal to g of x, and less than or equal to f of x, on some interval surrounding c, then if the limit of f of x as x approaches c equals L, and the limit of g of x as x approaches c equals L, then the limit of the middle function h of x as x approaches c equals L. Has to get pinched to the same value, right? Everybody agree? So that's our justification for that last step, right? Isn't that cool? That's just, to me, it's just a super cool proof. I mean, it's just a bunch of areas. You know, I think that's just, I really like that one. Just me, I like that one. So how do we go then? So I did a lot of work now, so you guys gotta do some work. Man, help me out a little bit here.
This is fun.
So how can we get from the limit of sine theta over theta as theta approaches 0 equals 1, how do we get from there over to the limit of 1 minus cosine theta over theta as theta approaches 0 equals 0?
I thought you were proving that
Well,
one.
no,
I was just waiting for that.
we proved this one, right?
Yeah.
We proved that one, but now that we proved that one, this one's just a gimme. We can just get to that one with some fancy trick.
Can we just use the arrow?
Sine
Theta plus cosine theta equals 1, and you just change the.
But how can you, why can you?
Because
Okay, you might even be able to argue here, if you could probably, I just thought of something, you could probably even come up with a pretty clever argument right here.
Oh, I was thinking of it. So if we know that sine theta on the third step from the bottom, if that equals 1, then if we subtract, nope, never mind. Nope, actually yes. Because if you subtract 1 from cosine theta, then it has to be 0, because it equals 1,
Okay,
but so cosine theta.
so everybody
equals
see
1,
that?
so
We
1.
probably could get to this using a similar kind of proof if from this step right here, what if we subtracted 1 from everything, right? Everybody see that? Okay, we could maybe get to this There's a way, we probably could make that work.
Well, actually.
I think we could, but we were not gonna have time for that. We probably could, we'd have to.
No, all you need to do is like just, I mean, it's not like super mathy, I guess, but logically, if cosine theta, the limit of cosine theta as it approaches 0 is 1, then if you have cosine theta be negative, then that'll subtract, and you add 1, and then you subtract the cosine theta, then that has to equal 0, because that's basically 1 minus 1.
Okay, so,
No, but but all that work that you had on there is applicable.
right, so I could, well, what if I wanna get 1 minus cosine theta over theta, right?
Yeah.
So I could subtract cosine theta from each part. That's gonna give me 0. I'm gonna get sine theta over theta minus cosine theta, right?
Yeah.
And then over here, I'm gonna get 1 minus cosine theta, right? Agree?
That wasn't what I did, but yeah.
Okay, if I divide everything by cosine theta, or just by theta, I'm gonna get 0 over theta. I'm gonna see if this, I don't know if this is gonna work. Let's just see if it would. So, yeah, second one is, it's gonna be a little bit tricky. That's gonna be like a theta, cosine theta, theta. It's gonna be a little bit tricky. I think you could make it work.
Isn't that excessive work? Because we can do it, like, if you go back to all the stuff that you had on it before, you don't need to do more work, it's just logical, I believe.
I think there's a way you could coax that out, but, well, I'm not gonna do it, because I think there's gonna be some, it's gonna take a little bit of time, and I'd rather do something else anyway. I'd rather do this.
Okay.
Being as we've already proved this guy, we should be able, without having to do any fancy geometric arguments, we should be able to just sort of reallocate that relationship in this form, right? Just by using trig identities. Go. There's not really probably one way to do this. There's probably a bunch of ways to do this. How could I start here and get here? How can I do some work on, gotta do some work on my, what are we gonna do?
Look up staggering one area.
What do you think? Ideas?
Isn't one of them define sine theta, plus cosine theta equals 1?
Sine squared theta plus cosine squared theta equals 1. Yeah, okay. Okay, so what if, okay. Go. What do you think?
You can't make square though.
I mean, maybe you could. I mean, normally we can't just square something, but if this limit's approaching 1, right, okay. So that's one possibility. I'm not gonna tell you. I mean, there's ways we could make any of these work, I think, but I want you to see if you can kind of power through this. If it doesn't work, we'll try a different route. This is real math, though. This is what you do in college when you're having to go through and do a proof. You know, a lot of times you're gonna go down some dead ends. Let's explore that, though. That's an idea. What if we then said this would be true, right? If the limit of hand equals 1 as theta approaches 0, then the limit of hand squared must also equal 1, right? Okay. So we could say this: the limit of sine squared theta over theta squared as theta approaches 0. How could I rewrite that?
Still equals 1.
Because
But we
sine
can rewrite that as 1
sine squared
minus
theta is equal to.
This is
1
gonna be pretty
minus
cool.
cosine squared.
This will work. This is one way we could do this.
Sine squared
This
theta
isn't the way I
equals
was gonna
1
do it, but it'll
minus
work.
cosine squared theta.
Okay, so sine squared theta is the same as 1 minus cosine squared, right? Everybody agree? Okay. Over theta squared. This is super cool. This is gonna work. I love this stuff. Okay, now 1 minus cosine squared. Is there a way we could factor that? Give you a hint. 1 is the same thing as 1 squared. How do we factor the difference of squares? Because cosine squared theta is really just cosine theta quantity squared, right?
1 minus cosine theta.
Ah, okay. Everybody see that? So this becomes the limit of 1 minus cosine theta times 1 plus cosine theta, right? Over theta squared. But let's do something tricky with the theta squared. What do you think? On the bottom, I just need something that's equivalent to theta squared. Theta and theta, right? How about if I make it theta times theta? See what I'm saying? And now what I've really got here is I've got the product of two quotients, right? Okay, well, let's take our limit. Would you agree that as theta approaches 0, what's going to happen here?
It's gonna go to 0.
It's gonna go to 2 over 0, which is.
It's going to go to, okay, it's going to go, we're a little bit ahead of ourselves on this one, just a little bit.
No, because we're working through all the math. It's
Yeah, I know, but we haven't talked about one-sided limits yet, but I'm going to do this anyway, because maybe this will help one-sided limits make sense when we get there. If I take this limit, in the limit that theta approaches 0, this is going to go to something like 2 over 0, right? Now, is theta ever going to be 0? No, it's not, is it? It's not ever going to be 0. It's going to approach 0. If theta approaches 0 from positive values, let's say we're approaching from the side where theta approaches 0 from 0.0001, right? Then what I'm going to get is, on the bottom, I'm going to get some small positive number. Agreed? Call it 0 plus. But it's a number. It's not 0, right? So if I get 2 divided by some very small positive number, what's the result of that?
a very,
Very small.
very, very
No, it'd be
big
large,
number.
because-
A very large positive number. Agreed? Everybody agree? Okay, or if I approach from the other side, I would just get a 0 minus. Right? If I approach 0 from a small negative value, then I would have a very small negative number on the bottom, and that answer would give me some very large negative number, right? Okay? Okay, but we know that this limit has to equal what? Has to equal 0, doesn't it? Right? Everybody see that? It has to equal 0. Well, if this is a very large positive or negative number, then what's the only way that we can get a limit that's actually equal to 0? Multiplying by 0, right? 0 times any number, any arbitrarily big number, is 0, right? You see that? Right? That's so, in a sense, we just kind of proved that, didn't we? Right? Could we have done this a little differently? I think yes.
Could we have done it a little differently in 2 minutes?
What if we had, instead of squaring both sides, what if we had just multiplied
By 0.
What if we had multiplied by sine theta over sine theta? Then on the bottom we would have had what?
Scientific.
We would have had theta times sine theta. Agreed?
You're not squaring them though, right? Or you
No, I'm multiplying by 1.
Oh, no.
I multiplied sine theta times sine theta and theta times sine theta, right? Okay? And then we'd end up with 1 minus cosine squared theta over theta times sine theta, okay? And if we were to, how's this gonna work then? I think that would work too. Okay, but how about this way? What if we could, it's kind of challenging maybe to try to go from there to there sometimes. But if you're having a hard time getting from this point to this point, we navigated it successfully. We did it, right? What's kind of a cheat though?
that way.
The way
Yeah, what if I just work from here to here, and if I can create a chain of algebraic steps that get me from here to here, couldn't I just invert those steps and get from there to there? Try that. Try that, because I'd claim it's easier to get from here to there than it is to get from there to there, just by using trig identities. Okay. There's a way I would have done this that we haven't touched on yet. Oh, we don't want to spend too much time on it, but just challenge yourself. I'll put an assignment up for this stuff, but just see if you can do that. See if you can get from blue to black. Okay?